Let's learn about the Laplace transform equation. So when we typically take the Laplace transform of some function, we denote it by a calligraphy L followed by a curly brace of some function, let's say x of t, where x of t is a time domain function. And this is going to be equal to capital X of x, which is a frequency domain function. Now, we can actually write x of s in terms of x of t as the integrand in some integral. So let's write that out. So if we have x of s, that's going to be equal to the integral going from 0 to infinity of x of t times e to the negative st dt, where s is going to be equal to alpha plus omega times I. So if we took the real part of s, we would get alpha, and if we took the imaginary part of s, we would get omega. Now, one fun fact is with the Fourier transform, that is actually a piece of the Laplace transform. Because remember back to the Fourier transform, it had this omega I term as the exponent. So instead of this negative st, we have negative omega I or j, here I'll just do I, times t. So it's actually a piece of our Laplace transform, but that's for a later video later on. Anyways, now that we have our integral form, what we can start to do is we can actually derive some of the Laplace transforms that are in our tables. So for example, if we had the Laplace transform of a constant 1 in the table, it's denoted as 1 over s. But how do they get to this? So what we can start out by doing is we can let x of t be equal to 1. Then capital X of s is going to be equal to the integral from 0 to infinity of x of t, which is 1, times e to the negative st dt. So taking the integral, we have 1 over s times e to the negative st evaluated from 0 to infinity, which gives 1 over s, which is negative, times e to the negative infinity, which is the same as 1 over e to the infinity. And 1 over anything incredibly large is going to be going to 0. And we'll have minus e to the 0, which is 1. So that leaves us with 1 over s. Now let's do another one. Let's say we have the Laplace transform of some constant capital A times e to the negative lowercase a times t. Well, that's going to be equal to capital A divided by s plus lowercase a. And we start this out by defining x of t as capital A times e to the negative lowercase a times t. So then capital X of s is going to be equal to the integral from 0 to infinity of x of t, or capital A e to the negative lowercase a times t, times e to the negative s times t dt. So we can start out by pulling out our constant capital A, and then we can combine the terms, or the exponents, in our e, essentially. So we'll have e to the negative s plus a, or lowercase a, times t dt. Then by taking the integral, we'll have negative capital A divided by s plus lowercase a, and then we'll essentially evaluate e to the negative s plus a times t from 0 to infinity. So then we'll have negative a divided by s plus lowercase a, and then we'll have e to the negative infinity, which is going to be 1 over e to the infinity, which will go to 0, and then minus e to the 0, or 1. So then, in the end, it comes out to be positive capital A divided by s plus lowercase a. So look at that. Now you can define essentially any equation into the Laplace or frequency domain by hand.